Well, I think we can start. Welcome back, everyone. We're about to close out week 11, and the fun fact about that is week 12 is the 75% mark. So we're rapidly getting through the semester. With what we have going on today, not a whole lot of announcements. Quiz 9 is due today. This one was the one that's due across spring break. So if you need additional time, I accept all the quizzes, even if they're late for full credit. No worries. And the quiz number 10 is posted. This one is based off the graphs and media section, unit 5D, that we're working through. We're nearly done with this unit, and then we'll have one more to get through, unit 5E. And after that, we're going to move from statistical reasoning into exponential growth type problems and exponential decay problems in chapter 8. But any questions or comments at all to start us out today? Okay, well, let's get started. So here's where we left off. A pretty challenging graph, but not the worst one that we have seen. But I did want to mention, I did make a revision on here. I just barely remember to upload it. There's also a revised version in the blank lecture notes folder that you can find as well. One graph I did want to change for the revision is this one right here. Let me zoom in on this a bit. I felt like this graph was kind of challenging to work through when we're doing the second part, redrawing it with the vertically stacked line charts without putting these numbers here that you see kind of small. So I'll make sure to read them out as we go. So that's the only revision. Same exact graph context, but I just changed the graphics on the graph itself. But aside from that, we were nearly done with this problem, but we decided to come back to it instead of rushing through it on Monday. This problem is about the net energy trade balance among 4 different major global powers in the year 2000 and projected in year 2040. The idea was if a bar is below the axis, that means the country actually uses more energy that it itself produces. So they have to purchase energy in some form or fashion from their neighboring countries. A blue bar is referring to the year 2020, and orange bars referring to the year 2040, so a projected value. And if it's above the x-axis, that means this country actually produces more energy than it expends itself, and so it's selling its energy on the global energy market. So we resolved a couple questions about which countries were energy dependent. It was just one, Norway. Which countries were net exporters of energy, meaning energy dependent, I got that backwards. Energy dependent, meaning they had to import energy. That was China, US, and Japan. The only one that was energy independent, the next exporter, was Norway itself. That was the part B. Sorry, I got those two mixed up. And we found that the country with the most significant change was US. If we put the graphs together from the very bottom of 2020, the very top of the projected year, this is going to be the longest one. So it had this most significant change. Well, any questions at all, folks, with the recap on this problem? Okay, well, part D is kind of a weird question. It's asking which country is projected to have the most significant reversal in their net energy trade. And it feels like a trick question because Norway didn't have a reversal. It was exporting in both of the time periods, 2020 and projected. China was energy dependent in both of the time periods, and so was Japan. There's only one country whatsoever with an actual reversal, and that was US, being massively, majorly energy dependent in the year 2000, probably because of a major oil imports, to projected being energy independent exporters of energy in 2040. So we would say here, the country is US. So most significant really wasn't a big part of this question. It's the only one that had an energy reversal from being dependent into independent. So let's just mention that as well in our answer. This is the only country on the graph with a reversal. Well, we've finished off this problem. Any last questions or thoughts about this one? Okay, well, just one more graph to get through. This section again is pretty tricky in a certain sense. A lot of these graphs can be not too bad, say just looking at geography essentially on this one related to different scales, or this one, which is just multiple bar charts we're looking into, to pretty confusing depending on what is actually being measured on the vertical axis. For this one, which was confusing in its own right because of different time periods and the fact that the axis could go positive or negative and have different meaning in either of these directions. So the next one, the thing that's new about this graph is just a lot's going on because we're throwing in two different variables at the same exact time. On this one, the units are depending on which variable that you're talking about. So this scale does double duty for us. Let's take a look into the context and then read through the graph in full to see what's going on. This one is all about the Idaho potato industry trend. And so it says, in the Idaho potato industry, the standard unit of measurement for production is the hundredweight. I didn't know that, so I learned a lot about this kind of stuff in this problem. The hundredweight is abbreviated as CWT, so CWT for hundredweight, and that's a pretty weird unit. Think of C here as being something along the lines of, like, say, a centimeter. Meaning 100. So 100 weight is exactly 100 pounds. And so that gives us an idea of what's going on in this production. So here we're just thinking about production in the 100 weight. A value of 100 million hundredweights, CWT, is 10 billion pounds of potatoes. So when we see in the year 1985 for production, that's the part in red, that's at 110 hundredweight, means it's over 10 billion pounds of potatoes produced in 1985. So that's the trend so far. It's not just about production. There's production in this red color, but there's also acres planted in blue. So that's the acres in thousands. So in 1960, in all of Idaho, 233,000 acres were planted in potatoes, and production was 4,300 weight. Then it becomes a trend as we look at this across the years. So that's our next variable to take a look into. And altogether, this graph is saying a lot. It may not be saying everything in the best possible way, but there's a lot we can look into when we see this graph. Any questions or comments about it? Okay, well, if you saw this random question, say as a quiz problem or an exam problem or a final exam problem down the line, and it asks you to comment on any trends you observe in the graph, it's a pretty tricky question in the sense that it's pretty wide open. Anything you say here that corresponds to what's really going on in the graph would be full credit. If I needed extra response, I might have to say, mention one thing for production, mention one thing for acres planted. But this one's pretty wide open. So pretty much anything you say that is true based on what we see in the graph would qualify for full credit. Any volunteers for anything you'd like to say that might jump out at you as you read this graph? It's a kind of a tough question in a certain sense, right? It being totally wide open, but it does kind of focus us on this aspect right here. It's asking about the trends that we might see in the data. So if we focus on one variable and then maybe the next, we can look into acres planted. And by trends, we're meaning what's happening to the acreage planted as we go from 1960, going by 5 years, all the way to 2020. It looks like it's not perfectly always going up, but slightly gradually rises, dipped down from 1975 to 1980, but then went up again. It seems like the peak year is around year 2000. Then it starts to drop a good amount and level off. So anything along those lines that you mentioned would be a good way to observe a trend for acres. So we could say for acres, the amount rises steadily until its peak. This was 2000, Idaho had the most acreage planted for potatoes. It drops, but it seems to somewhat level off a little bit between 2010 and 2020. It went down a whole bunch for a whole decade, then went up a little bit, down a little bit, but somewhat about the same amount across these 3 years. So if we wanted to add that in, we could say that levels off between, that was 2010 and 2020. So that's the story so far with acres planted. It's not the whole story in the Idaho potato industry. There's also how many potatoes was produced, the production. Again, in its complicated unit, the hundredweight. And that might be one thing that we might not be so happy with when we look at this graph. It's nice in a sense that there's just one vertical axis. It's for both units, acreages and production at the same exact time. But notice the effect that it causes. The scale going up to 500 is more natural for production. It only went up to 500 because it was going by hundreds, and we want to exceed the 411 value is the only reason it went that high. But scale going as high as 500 is not as appropriate for total production. That's because total production only gets to 152. And so when we throw it on this kind of scale, it's not easy to see the production trend. It's sure it is going up like before, maybe leveling off like before, but that whole scale has been compressed by a whole lot. It's hard to see the actual change now. But let's still do the best we can and mention for production. It has a similar trend of it's increasing steadily until looks like it peaks in year 2000, which was about the same as the peak for the area, the amount of acreage planted in area. It doesn't drop off as bad either. It dropped off a little bit. It was pretty level. So it peaks at 2000 and stays about steady until 2020 is probably the better story there. And no, actually looking a little closer, without seeing those numbers, I would have never noticed that. The peak is actually at 2020. It's slightly higher than the 2000 value. So we can say for production, it rises steadily. And let's say it differently, and peaks in 2020. I don't have the 2025 data in this chart, so no idea what's doing right now at this time. But for the historical data, that's the story for production. It's always gone up, except around 2000, it's pretty level, just gradually going back up to a peak of 154. Well, any last questions or thoughts looking at this graph? Okay, like before, there's a whole lot of stuff that you could say on this graph. We focus mainly on the trends to match the direction of the question itself. The other things you might have said along these lines is you notice that acres planted peaked majorly in the year 2000, but then it fell off by quite a amount. It's like 75% of the 20,000 value in the year 2020. So even though acreage plantage has gone down by a lot in some of these years, production was just still steadily increasing. So something new happened, probably different technology, different pesticides, different kind of fertilizants, and all sorts of things were being developed here to keep production going up, despite acreage plantage actually going down. So again, there's lots going on with this graph. It's not the worst graph in the world, but there are some complaints about it. It probably was not appropriate to put two bar charts together like this on one scale that went to 500, when production itself peaks at 154. That seems like the scales are just not compatible, really. It wasn't as bad as of a problem as what we were seeing here on example 2, where producing a graph like this intentionally could be thought of as being just completely unethical and dishonest with the data. This we had lots to complain about. So our current graph isn't as bad as this one, but still it could be improved. And so that's what the next part B is going to be all about. Before we improve this graph, any questions or thoughts about it? Okay, so this is the part of the notes where I realized my graph just didn't have enough detail to do part B. I tried to do this by hand, but I had a hard time just estimating the heights of these bar charts. And I felt like my estimates were such wide errors on them that the charts that I was trying to produce by hand really weren't making the sense that I wanted to. So this has been revised to give the values on here. Again, sorry, it's kind of hard to small to read these. I'll try to keep this zoomed in as much as possible. So what we want to do is redraw this whole graph vertically as vertically stacked line charts, one line chart for acres planted, and a separate line chart for total production. We're going to stack them so they're easy to compare against, but we're not going to try to keep them on the same set of axes. And by line charts, all we're meaning is we're going to draw dots to represent the heights and draw line segments that go through each one of these dots, as opposed to having bar charts. So let's give that a try. Doing this by hand is definitely tougher when you're doing this in my lab. Essentially, you're selecting by multiple choice the correct graph amongst them. And if this was a true exam question, I probably wouldn't have as many bars. I'd probably keep this well contained so it doesn't feel like we're spending too much time on just one problem. But nonetheless, let's do the best we can on this one. I'm going to try to go down here, put this below for reference as we go to plot. First thing I want to do is actually put down the stacked line charts. So I'm going to set the scales like this. We want them to be the same proportional size. Because we want to compare one variable against another. It doesn't have to be perfect. This one's a little bit longer, but we'll just go with that. Next, we're going to separate out the variables, acres versus total production. So I'll start with the top line graph, acres planted, or the graph down below. Let me see if I can insert just a little bit of space. This one is going to be total production. So those are the chart titles. I put them off to the right so I can just kind of fit them. Next, we need descriptions of the vertical axis, much like if we were doing, say, a histogram or a bar chart in the prior section. So the first one is going to be acres in the thousands for acres planted. Let me see if I can fit this all here a little bit better. acres in thousands of acres. And let's put it in the range as well. I think going by hundreds, that still should work out well for us. The data peaks out at 411. So if we go by hundreds, we would end at 500 like we did before. So this will be 1, 2, 3, 4, 500. And let me try again to spread this out just a little bit better. So 1, 2, 3, 4, 500. Okay, so we got one vertical axis done. We'll focus on the next one for total production. And this is in millions of the hundredweight. Let's put in that abbreviation, CWT. Now this one goes differently because once again, it peaks out at 152. So this time we can maybe go from, how about maybe 25 should do the job. This would be 25, 50, 75, 100, 125. So the scales should be about the same height on both ends. For vertical and horizontal, same length. Now we just need to put in the common horizontal scale. We would need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 tick marks on both of them. So let's put those in. I miscounted, possibly. Let me double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Then we'll do our best art we can, put them down again. And try to line them up so that they are vertically under each other. And this is a lot more tedious than I realized. We need to put in the years. So let's go 1960, 1965, 1970, 1975, 1980, and so on down the line. Yeah, definitely if this is going to be an exam question, I'll make it less bars so it doesn't feel like we're spending like 20 minutes on just one single problem, reflecting a little bit more on this one. But we're getting there. We're almost done with the axes. 2005, 2010, 2015, and 2020. One more time. So same years, 1960, 1965, 1970, 1975, 1980, 1985, 1990, 1995, 2000, 2005. My hand's legitimately getting tired at this point. 2010, 2015, and 2020. Okay, we're about there, about ready to go. So what we want now is, now that we have both of the scales, we can put in the vertically, they're now stacked line charts. Any questions whatsoever, folks, with just the setup aspect? Okay, well, let's do acres planted next. And just so that we can see these numbers a little bit better, let me take one more screenshot. I want to just take off the top here because I'm mainly just going to focus on these numbers we see. If I could get that top lobbed off. There we go. Okay, so going down the line on those values we see, the years start at 1960. So this is at a value of 233. So 233,000 acres planted in that year. So that kicks off our line chart. Instead of putting down a bar, we're just putting down a dot to represent the entire bar. Then at 260, this is for 1965, we're about here. And then so on down the line, 312 in 1970, 335, 1975, then 325. So it went down just a little bit in 1980, jumped to 360, 390, so just under 400. Then right at 400. Here's where we're peaking out at 411, so just slightly higher in the year 2000. Then dropping by a whole lot. So now back to 375. So that would be about here. 315 in 2010. Yeah, this gets kind of hard to estimate once we're pretty far from that vertical axis. So you could do dashed line segments going all the way down, but just do your best job to visually estimate. And I'm not going to be super picky on these. So that was the 315. Then it jumped a little bit higher, 320, then back down to height 300. So to make this a line chart, what we do is we do vertical line segments, or excuse me, straight line segments going like this. We don't let it curve because that would be saying we know something about the data in the in-between years. So if I went a little fancy and some reason curved it like that, it might look kind of nice as a smooth curve, but I'm saying something with some of these peaks and the values, like I know data that I actually have no idea on. So we only do straight line segments to connect just the known data values. So going through like this, roughly, gives us that line chart. So finally, that's acres planted. That tells us pretty much the same story as what we saw on the original bar chart. But the major improvement is going to be in production. Again, it was kind of hard to see what was happening in this trend because it was all compressed down using the wrong scale. Our scale should only really go up to 125 if we're going by 25s. And so this is going to give us a better view once we fix these data. So let's take that part off. And one more run, this time focusing on total production values. So production started off pretty low in 1960, about this height, shy at 50, jumped to 62 right after, then 79, 88 to 1975, then 91 in 1990, and finally we're way out here, we're up to 110, then 125. Oh, hang on, I for some reason stopped at 125. It needs to go a little bit higher, right? Let's keep on going up here. Our data extends to 150. And let's go up to 175. Sorry for that short omission there. Our scale might look a little bit different because it's taller than this vertical scale, but let's go with what we've got. So that was the 1985 value at 110. Now we're at 125 on 1990. 138, so slightly higher. Year 2000 was 152, so it jumped a good amount there. Now it's kind of leveling off. So 2005, slightly lower. 2010, slightly lower again. Then 2015, back to a height of 150. And this was its peak in 2020, 154, so just slightly higher. So that's the story for total production. then it becomes a bona fide line chart once we just essentially connect the dots. But once again, using only straight line segments between each dot. And we got it. That again was a little bit more tedious than I kind of realized. I probably should have toned down this graph, but at least we have it. This is now the line chart, which represents the original data up above. Any questions at all, folks, producing the line chart?
I just have a question about when we do our test. Will you allow us to bring in a ruler so we can do our line graphs better?
Yeah, absolutely. And let me make a note of that since the testing centers can sometimes be pretty particular. So let me put down here. I'm going to write this in for each testing center that I send this out to. Allow for a ruler on exam 3 and the final exam. So in case you have to do this, yeah, that'll make the chart come out a little bit nicer. Kind of wish I had a ruler, a dashed lines that was going across to be a little bit more accurate. But I'll also say a ruler is not going to be required. It's going to be really up to your preference. Might be a little bit faster, more satisfying to actually use a ruler. If you freehand it like I did and it's just a little bit off, I'm still going to give full credit.
Thank you.
Yep, absolutely. Thanks for asking about that. I'll make sure that that's put into the allowed materials on the exam. Other questions at the moment? Okay, well, there's one again, just like this in MyLab, but it's a little bit less tedious in MyLab because what you can do is go on a bar by bar segment and they give you multiple choice on graphs and just eliminate the graphs that are wrong. Maybe a point is too high, too low. It could be a wrong graph because the scales, one or the other, is just incorrect, something along those lines. As you could tell which graph is right just by elimination. So the harder challenge is to do it by hand like this. But once we get there, follow question asks us to briefly discuss the advantages of multiple line charts over the original display of the data. And I guess there's a lot you could say here. I mean, there's less visual noise if you're looking at just one variable against the other in this kind of way. The one thing I mentioned was mentioning all along is one major advantage of the stacked line charts is that we can see the trends or trend for production better by giving it its natural vertical scale. Meaning trying to visualize production from 0 to 500 really didn't make sense. And you can imagine how this could be even way off if it was two other different quantities and maybe one is just astronomically larger than another. These purple bars might have been just all very close to the horizontal axis, and you really wouldn't be able to get any information at all. So it could be an even more exaggerated effect than what we see here. But now we see both of these together, and if you can see the trend better in total production, then you can see how one is correlated with the other, how as acreage planted went up, so did total production. But something kind of amazing happened in the year 2000 where acreage goes down, yet we're seeing a little bit more clearly total production stays stable and even goes up just by a little bit, even with falling year after year acres planted. So you could add that as a different take or a different analysis on this one. But any last questions or thoughts on what you'd want to put down for this one? Okay, let's maybe add that last thought to round out this question. We can say here, we can see more clearly that production remained stable in years 2000 to 2020, despite acres planted falling, going down pretty steadily year after year. So that effect, I think, is a lot more pronounced when you see the stacked line charts versus when you're seeing it here. I think you have to stare a lot harder to see that same information on this graph, whereas here, it's a little bit more apparent, in my opinion. But we did it, folks. I think this section, it was kind of challenging because a lot of the graphs can get very, very involved, as we've seen. Some of the scales can be more tricky than we might expect. But any last thoughts or comments before we take a look into the final unit of this chapter? Okay, well, let's open up that final unit. After we get through this last one, 5E in chapter 5, we'll be switching gears into concepts with exponential growth, exponential decay, which is going to feel kind of familiar because we were kind of looking at that when we looked at compound interest. But first, here's our last unit. We're going to look into two more topics in statistical analysis: correlation, causality, and that's going to round out our chapter. Chapter 5 has been pretty interesting because it's all been kind of surface level as far as the statistics have gone. We haven't done any strong statistical methods. We haven't cranked out any big formulas. And so to really get in statistics, you'd want to take an introductory course, statistical reasoning. But our quick short time here in chapter 5 gives you a good overview of some of the topics that you would be getting into. And this is, in fact, one of those topics. Here, we're looking into correlation between two quantitative variables. We'll say correlation exists between those two variables when higher values of one variable are consistently associated with higher values of another other variable, or when higher values of one variable are consistently associated with lower values of another variable. And notice it keeps on saying higher values of one variable on both cases. That's kind of hard to highlight. So let me just highlight it this way. When it mentions correlation, it says in both cases here, higher values of one variable associated with either lower values or higher values of the other variable. The reason it's said in this kind of way is we think of one variable as always being on the vertical axis. We always read it left to right. So we're always going from lower to higher. So we're saying if the horizontal axis is going from lower to higher, the values in the vertical axis are either consistently going up, going higher, or consistently going down, dropping down lower. So if that's the case, and a certain plot, we'll say that that there's a correlation between the variables. The plot that reveals this is the scatter plot. That's the plot that we're seeing down below. It's different than the line chart in that we don't connect line segments whatsoever. In the scatter plot, we're just looking at a graph at which each point represents the values of two quantitative variables. So if we, for example, took a look at this scatter plot, there's a quantitative variable, resting heart rate, another one, VO2 max. If we look at just say 1 point, this one right here, it should correspond to just one single row in the overall data table from which the scatter plot came from. So we would look into the resting heart rate column, find our 75 value, here it is, and it should correspond to a VO2 max value of just below 30. So here it is at 75, and if we go to the left, it is, in fact, just below 30. So that's all the scatter plot is doing. It's taking two quantitative variables. When we drew a histogram for our quiz problem and in the prior 2 units, that was with just one single quantitative variable together. Now, if there's two in the mix, the scatter plot is a great way to visualize this new variable. Well, any questions, folks, with the definition of correlation or scatter plot? Okay, well, this section is going to be a little bit shorter. It's kind of in the similar vein of what we did in just the prior section. However, we're just really focusing on one kind of plot, the scatter plot, thinking in terms of correlation and in causality for the last example. So let's read through this context, see what's going on, and then see if we can answer the questions below. We're told to start this out. A university sports science laboratory is conducting a study on cardiovascular efficiency. We're told that researchers want to understand the relationship between a person's baseline heart function and their maximum aerobic capacity. So when they say baseline heart function, sounds like they're talking about resting heart rate, and maximum aerobic capacity probably means VO2 max, but that's a pretty complicated unit, so we'll look into that more. And next says, to do this kind of investigation, here's what they specifically did. The researchers measured each athlete's resting heart rate in beats per minute after having them sit quietly in a temperature-controlled room for 10 minutes. So a very specific kind of resting heart rate. It's not like your resting heart rate when you're actually sleeping at night. So they put them in a box, temperature-controlled, and had something read their heart rate, took an average value after 10 minutes. And these were their values. Some people are pretty much on the lower end, which might mean they're potentially more fit people. Some people are on the higher end, which might mean they're less fit, but that's what they're trying to investigate in the study. So to investigate their fitness, they're looking into this next variable. So here's the next layer of the study. Next, each athlete completes a rigorous treadmill test to exhaustion while wearing a respiratory mask. This is a heart test that has been done if you have any kind of cardiac issues, kind of an infamous test. The treadmill determines their VO2 max in milliliters per kilogram per minute. So it's in millimeters of oxygen that was moved. So they measure that through the mask. Per kilogram, how much the person weighs, their biomass, in other words. And this is for fairness. A bigger person might have bigger lungs. A smaller person might have smaller lungs. So this gives us a baseline comparison of how much air per biomass of the person per minute. And so that's the VO2 max unit. It represents the maximum rate at which their cardiovascular system can effectively consume oxygen. And they found that maximum rate because they would exercise you to exhaustion, to the point at which you're about to pass out. Again, a horrible test, but still done to this day to determine VO2 max. So that's what they did. They looked into baseline heart function, your resting heart rate, with the assumption that the lower your resting heart rate, the more fit you are. But then they actually measured fitness through this variable on a treadmill. And when they took all of these data together and put them in a scatter plot, here's the output. Each blue dot represents one individual. Well, let's see what we can say about this. It says to describe the correlation and the strength. So first question would be, or correlation direction. Echo says, I think I'd have a heart attack. Yeah, that's probably a pretty reasonable assumption. Unfortunately, this was done in the past as well for people who were at risk for a heart attack to see how well their heart was functioning, which again sounds counterintuitive because that's really kind of stress testing a heart that is suspected to have issues already. So thankfully, science has kind of progressed beyond that for people who are at risk for heart attacks as well. So when we were talking about correlation, we were talking about there's correlation between two variables. If one variable increases and consistently the other variable will increase, or when one variable increases and consistently another variable decreases. So would you all say when you see this graph, does it look like correlation to you? We'll think of, say, the resting heart rate increasing. If the resting heart rate increases, what would you all say happens to VO2 max? Does it go up or does it go down? As we increase heart rate. Yeah, I agree with Amy. It's not perfect, right? There's a lot of scatter here, but it looks like if you're on the lower end, you're pretty much going to have a high VO2 max. There's an exception here. There's one person at 60 with a low VO2 max. Higher VO2 max means higher physical fitness. And as we move to the right, here's higher resting heart rates. VO2 max seem to be mostly lower. Again, there's some exceptional values. This person in particular has a high resting heart rate and a pretty decent VO2 max value. And this person is even more off, really low resting heart rate, but super high. Or hang on, that's what we wanted to see. This is the one that was a little bit off. Let me highlight this one to not get mixed up again. So this one looks about right for the trend. This person has a low resting heart rate, yet their VO2 max is a little bit higher. But when we look at this person stands out quite a bit. Their resting heart rate is low and their physical fitness, VO2 max, is low at the same time. Yet if we try to draw a line through all the points, not a line that kind of connects like a line graph like we saw before, who knows what we'd be drawing, but just a line that tries to get close to all these points, the line might look something like this. It's a line that goes down. So as you read the graph from left to right, the dots, maybe not 100% consistently, there's some odd ones in here, but more or less, they are falling down. So I agree with Amy on that assessment. We can say here, there is a correlation in the negative direction the points are going downwards. As we read the graph left to right, the typical way we would read it, let's say here just in the parenthetical, points moving downward. We also want to assess what is the strength of the correlation. It's not the most fair question right now because this is just our first scatter plot that we've seen. So we'll see others that are no correlation at all. We'll see others that are very high correlation. But for this one we see here, we would call this one either moderate, kind of in the middle, or weak. It's just a visual assessment, so you would want to avoid saying very strong or strong in this assessment. Here I'll say the correlation is weak, which is kind of unusual, interesting in this study. They probably had a good feeling that there'd be a higher correlation between baseline heart function and overall physical fitness, but it sounds like there's probably more to the story here. There's probably also confounding variables. They were put in a room that was, again, they had to sit quietly in a temperature controlled room for 10 minutes. But, for some people, if you tell them to just sit there for 10 minutes and do nothing, that could be an anxious thing. They could be a restless person, for other words. So there's some people whose heart rate might just go up because you're asking them to do something that feels unnatural. Sit still for 10 minutes is not easy for every single person in the population. There could be a lot of other things that aren't controlled in this experiment as well. But nonetheless, there was a slight effect, a slight correlation in these data. It says here what conclusion can be drawn from the scatter plot. We can say that there is a weak association between resting heart rate and VO2 max, but there are many other factors that can influence both variables, not just VO2 max, but resting heart rate itself is kind of a finicky measurement in the very first place. Well, any questions at all though, folks, with our first scatter plot of the day? Okay, really this plot was mainly just for us to introduce the topic of correlation, the direction of the correlation, and the strength of the correlation. But to really make some of these ideas a little bit more firm, here's the next set of full definitions. When we look at two different variables, say arm span versus visual reaction time, the things we want to look into for the relationships between the two are, if there's a positive correlation, that would mean both variables tend to increase together. That wasn't this case. One variable increased and the other variable decreased, so we said the correlation was in the negative direction, not positive correlation. We'll say negative correlation occurs when the two variables tend to change in opposite direction. So that was the negative correlation graph that we were just looking into. When heart rate increased, VO2 max tend to decrease. So that one was changing in the opposite direction, with one increasing while the other decreases. So that gives us negative correlation. Positive correlation is just the opposite, both of them increasing. And it's possible that you did a study and the two variables that you're interested in, even if you suspected they might influence each other, they might have nothing to do with each other. And that would be a graph conveying no correlation, no apparent relationship between the two variables whatsoever. We also had to assess the strength of the correlation, which was kind of unfair on example one. We never even defined it. But here's what we mean finally by the strength of a correlation. We'll say the more closely two variables follow a general trend, the stronger the correlation. It can be either positive or negative. So a very strong correlation means all the data lies very close to a straight line. So if you want to assess the strength of a correlation, try to just draw on paper. If it's a real quiz or exam, you can do that. If the points were really close to this, we would have called it a strong correlation. So suppose the points were the ones in red, not the ones in blue. If that was our graph, we would have said either strong or very strong if that was what the data actually looked like. But the scatter was way more severe than that, so we might have said moderate to be in the middle, or just weak in this case. I would accept either moderate or weak because we're all doing this as just a visual assessment. We don't have the correlation statistic that we're computing, so all of it is subjective in that sense. So that's what's going on between positive, negative, no correlation versus the strength of a correlation itself. And that's why we said that this one was weak. Any questions with those definitions so far? Okay, well, here's a brand new fictitious study to take a look into. And this is an interesting field of study, kinesiology. I might have pronounced that wrong. Let me know if I've said that wrong. Kinesiology is the scientific study of human movement, performance, and function. We're told that at its core, kinesiology explores how and why the human body moves the way it does. So now we're getting closer to the actual context. The kinesiology lab at Idaho State University is conducting a baseline physical assessment of 100 student volunteers. So that's why we see a lot of data here. There's 100 dots. If you were to count them, if you came short, it might be because one dot is really close to another one, kind of overlapping, which can happen on a scatter plot. The researchers want to investigate if a person's anatomical size, their height, their measurements, and so on, has any relationship with their central nervous system's processing speed. Amy says, while that must be a weak correlation, those dots are all over the place. Yeah, absolutely. That's what's going on with this one. In fact, we would say it's even worse than weak correlation. This would be the graph for no correlation whatsoever. If it looks like just white noise, and we can't put a line down that has a particular direction like this one, this was a pretty noisy graph too. There's a lot of scatter between the points, but it's kind of going down. There does appear to be a relationship here. But this one, I can't see an upward trend. I don't see a downward trend. There's no line really that describes this except maybe a flat horizontal line like this. If all you can put down is a flat horizontal line, this is no correlation whatsoever. And you know what's kind of surprising to me, but the more you think about it, they're trying to relate central nervous system processing speed. So they have to have a good way to measure that with how big a person is, their anatomical size. And so the more we think about that, I don't know if your central nervous system is faster or smaller, if you're bigger or smaller, or vice versa. This should be a picture of no correlation. So going on to the next level of the study, it says, first, they measured each student's arm span in centimeters. So that's going to be their anatomical size. That's why we have here arm span centimeters. So this is people at 150 centimeters all the way up to 200 centimeters for how far they can hold their arm from fingertip to fingertip. Now they have to measure central nervous system processing speed. That seems like a hard variable to measure, so let's see how they did it. It says, next, they have each student sit at a computer, complete a standardized visual reaction time test. This is nervous system processing speed, which is probably very, very multifaceted. So they're just looking at a thin slice of what that would really be. In this test, the screen flashes green, and the student must click the mouse as fast as possible. So there won't be any tricks there. Green just means click. They're recorded their average time in milliseconds. Probably they had this go off for maybe 20 flashes. They averaged the 20 reaction times. And these are their visual reaction times in milliseconds. And just for reference, on an internet connection, if you're on this end in milliseconds, that might be noticeable if you're playing a video game, for example, if you're at this higher end. So that's what they did. They looked at their anatomical size, how wide their arm span is, visual reaction time, how fast they could click a mouse button when a green screen flashed, and that's the data they got. So we want to describe the correlation, direction, and strength, but that's now a trick question. Once again, if you see something like this and you can't put a line that's either going up or going down that seems to fit the data, this is a graph of no correlation. And because we said no correlation, it also means there is no strength to describe. We only describe the strength of a relationship if there is an honest correlation, if the points are moving upwards or if they're moving downwards. But here, nothing's happening, so no correlation whatsoever. Well, any questions or comments so far, folks, on this one? Okay, well, there's really three things that can happen. There's either a correlation that's positive or it's negative, or there's none. So this is the graph that conveys no correlation whatsoever. And when you look at this kind of graph, then you can still make some great conclusions based on what you see. No correlation is important on its own. Any volunteers for a quick statement to say based on this graph, if there's no correlation?
Could you just say that the arm span has no bearing on the visual reaction time?
Yeah, absolutely. Anything along those lines would be great. You could say there's no effect between the variables, there's no relationship. Let's say it the way you said it. The arm span has no bearing on visual reaction time. So that's directly what we see with the no correlation. You could add more if you wanted to, but I would say that that's a complete response. If you want to say more, you could go back to what their original apparent hypothesis was. They want to investigate if anatomical size has any relationship at all with processing speed. And so you could add an extra statement that says there is no evidence of a relationship between anatomical size and, let me double check how they said that. I'll just say central nervous system processing speed. I'll abbreviate that to processing speed. In these data. And again, I'm not asking for a certain level of response. If all you said was the first sentence or something along those lines, I'd say that's great. If all you said was the second sentence or something along those lines, conveying the same thought, then that would be a complete response as well. And so this is just two different ways to say pretty much the same thing. There's just nothing going on with this data. But, that is informative to the sciences as well. So we would have to applaud them for making the effort happen. And maybe they should look into something different. Maybe they're looking at this all wrong. Maybe change the hypotheses or change the way they're making the measurement. Maybe there really is an effect, but they have to be more creative in determining it. This just didn't do it the job. They're one experiment here. Well, this is some of the couple main graphs that we've been looking at. For the next one, here is a new correlation that we're going to look into. This is going to be one that has certainly a positive direction. Looks like it's pretty strong as well. But before we get there, here's a couple more layers of the context and definition that's going on in this section. This is a section about correlation and causation at the same time. And so we want to start thinking about causation now that we're looking at these things. There's various reasons why correlation could exist. Correlation could just be simply a coincidence. And that's an unfortunate thought, but when you run an experiment like, say, on example 1, and I think there were 15 students in this data set, it is random data in a certain sense, and rare events can happen. It could have been just because something rare happened, effect was shown on the data, but the data really would have looked like this if there was 100 student athletes. So it could have just been all a coincidence that we found a negative direction in this one experiment. How do we protect ourselves from a coincidence? They need to replicate this study, maybe with a larger sample size that will refine the strength of the relationship, the nature of it, or if it's really this, no effect is really happening between the variables. So an explanation for correlation is, sadly, that's a fluke in the data. The data is random, and so rare events can happen. For a sample size of 50, that data might not have been a real effect. Another explanation for correlation is both variables might be directly influenced by some common underlying cause, meaning there might be something underlying the variables that's influencing them both. There could be, say, a lurking variable influencing the others. So if we think back on example one, when we look at between the correlation between resting heart rate, VO2 max, a lurking variable could just be how much training these athletes actually have. They're amateur athletes, but amateur doesn't mean that they're not putting in a lot of work. We might measure a lurking variable of how much time do you train as an athlete in terms of hours per week. And that could definitely affect your resting heart rate. And it definitely can affect your VO2 max. It could be the major variable that we should have been accounting for in the very first place, how much training is being put in. So there could be some other variable influencing all the others. And that could be the reason we see the correlation. The study could have just missed it, but the variables are still being affected by each other through that common underlying cause. And this is the one that the study is often trying to reveal. The third cause for correlation is that one of the correlated variables may actually be a cause of the other. So this is us trying to assess causality between the two variables. Even in this case, it could be only one of several causes. There's a lot of factors, for example, back to the first graph, of what can affect VO2 max, not just resting heart rate. There's lots of things that go into that. Human biology is very complicated, so lots of influences. So even if resting heart rate causes a change in VO2 max, it might be a small effect, and there's other bigger causes. So these are the three explanations for correlation, and we'll investigate this further in this particular example here. Looks like it's a kind of an agricultural example, stem diameter versus total plant height. We'll look into more about cause and effect, guidelines for establishing causality, and look at this graph. This is a pretty realistic graph, in fact, of number of firefighters responding to a fire, estimated property damage in thousands of dollars. And even though this is a silly example, you can imagine swapping these variables for something else and just accidentally thinking one variable has caused the other. This is our real correlation. It's probably moderate, not quite strong, but we definitely don't want to accidentally say firefighters in higher numbers cause higher property damage. That's not the case at all, right? There's other variables absolutely to take into account here. So this is our start in looking into cause and effect. We'll begin looking into that with example 3 and end on example 4. But I think this is a good stopping point for us now at this point. Any last questions or comments at all, folks, before we turn to the weekend? Okay, well, we'll finish these off when we come back on Monday. Then we're going to start our new chapter in chapter 8, exponential growth, exponential decay. Also on the Friday of week 12, that's when we'll start producing the exact coverage of what's going to be on exam 2, the formula sheet, and the sample exams, just like we did on exam 3. But so far, it's going to be kind of an ordinary weekend. We'll have another ordinary week next week on week 12. But have a great night, folks. We'll be back to it next week. Take care.